Uh, Vandana, ma'am.
Yes, Dr. Priya.
Yeah. Could you please even share me that YouTube link? Because what
Yeah,
happens is I
yeah,
parallelly open YouTube on my phone so I can see what people are seeing. Right?
yeah, yeah. I'm just sharing.
Yeah.
I think we can begin.
Okay. Should I start? Okay.
A very warm and hearty welcome to one and all on behalf of Gargi College. Myself, Vandana, from the Department of Physics, along with my colleague, Professor Shashi Chawla from Department of Microbiology, are delighted and privileged to welcome the August gathering.
Okay.
We have with us Dr. Priya Hasan. Am I audible? Am I audible?
Yes, yes, you are.
So we have with us Dr. Priya Hasan from Maulana Azad National Urdu University, Hyderabad, many esteemed guests, faculty members and dear students. Today we have a session on a talk and demo session on exploring exciting worlds of exoplanets, which is being organized under the aegis of National Academy of Sciences, India Science Society program. And this will also provide an opportunity for the participants to take part in a global activity by IAU OAD, International Astronomical Union Office of Astronomy for Development. We are thankful to our principal, Professor Sangeeta Bhatia, for her ever encouragement and support for the organization of such events. As always, best wishes of Professor Ajoy Ghatak, President NASI, are with us. We are grateful to Professor Anurag Sharma, Emeritus Professor IIT Delhi, and currently the Vice President and Chairperson of NASI Delhi chapter, for his immense support as advisory member for the program, and he will be joining in between if he gets time because he is busy with another meeting. The question always intrigues us all, whether we are alone in this universe. Ever since the discovery of telescopes almost 4 centuries ago, the pace of scientific and technological advances has been remarkable. From getting to know about our blue planet as a part of our solar system, explorations are on for the hunt of other star planetary systems. The planets of other solar systems are being detected, and this talk will enlighten us about exoplanets and the method of their detection. I take this pleasure of introducing Dr. Priya Hasan to our participants. Dr. Priya Hasan is an assistant professor in physics in Maulana Azad National Urdu University, Hyderabad, India. She did her integrated masters from the Moscow State University, Moscow, Russia, PhD at Osmania University, Hyderabad in 2004, and postdoctoral research in France and Ayuka Pune. She was awarded the Women Scientist Award by DST in 2006, and she has presented her work in various conferences in India, Europe, and US, and in the United Nations, Vienna. Her research interests are in observational astronomy, star formation, star clusters, and galaxies. She is actively involved in Olympiad, public outreach, and science popularization programs and has worked on various projects with the IAU OAD, US Consulate Hyderabad, etc. She is the co-chair of Women in Astronomy WGIAU and the member of the Public Outreach and Education Committee, Astronomical Society of India, and ISDT TMT. Dr. Priya will take a session of about an hour to be followed by a demo of analyzing the data using TopCat. In the last part of the session, she will also provide instructions for participating in Name the Exoplanets IAU OAD, that is a global event. So I invite our esteemed speaker, Dr. Priya, for her much awaited talk. Thank you so much, and over to you.
Yeah, thank you, Valdana ma'am. Thank you so much. Thanks so much for inviting me and giving me an opportunity to talk to the students. Thanks a lot. So I'll start off with what is our topic for today, which is the exciting world of exoplanets. And like Vandana ma'am mentioned to you, the session is made up basically of three parts. The first part will be in which, yeah, okay. So is my screen getting shared? No. I think I'll have to share.
Yes, it is being shared. You can go to the presentation or slideshow mode.
Yeah, now I think it's fine, right? Yeah, so like Vandana ma'am mentioned to you, the session is made up of three parts. The first part is where I will introduce you to the exciting world. Oh, I spelled it wrong. This is the exiting world. I'm sorry. I've made a mistake over here. So let me made it the exciting world. That would be really, that's really sad. Okay. So I'm going to talk about the exciting world of exoplanets. And you've been hearing a lot about it, I'm sure, in the news as well as other sources. And that's why I thought it was a good opportunity to let you know about what's happening in the world of exoplanets. So I'd first talk to you about that. After that, we'll have a short Q&A. Then I'll be doing a demo session where I'll show you some of the data that is available to everyone, over the internet. This is Kepler data. I will show you how you can analyze that to actually get parameters for a single exoplanet. And after that, I'll be introducing you to the IAU contest, which is on Name the ExoWorld plot contest, where I hope that your college could be a team and you can actually participate in that, and that would be a fun part. So first of all, let's just get on to exoplanets. So as of September 2022, there are more than 5,000. There are 5,157 confirmed exoplanets in 3,804 planetary systems, with 833 systems having more than one planet. It's not plane, but planet. I'm sorry. I think I just changed these things at some stage, and that's when this happened. So that's planet, not plane. So let's start off with our main thing. Why do we look for exoplanets? What is the purpose of our thing? So this is a quote which I really like very much. This is written by Carl Sagan. It is part of a book as well as a movie called Contact, one of the best science fiction movies of all times. And in the movie, there's a scene where, when asked, why do we actually look for aliens, right, for extraterrestrial life? This is what Carl Sagan says, that the universe is a pretty big place. And if it's just us, it seems an awful waste of space, right? Which is a very, I would say it's a very convincing argument as to why do we actually need to look for life in outer space, for the simple reason that the universe is huge, and to assume that it's just for us is obviously absurd. So when we do have this multitude of the universe, we do need to look for it. So if you want to actually look for alien life, the first step would be to actually to look for exoplanets, right? You want to look for their habitat. Where are they, where are they residing? And the first thing is to look for that. So this is an image of a Tatooine, which is one of the planets which is there in Star Wars. Many of you all who are science fiction fans would know this, where you have a double sun. This is this thing where you had a double sun, but in principle, this thing. So if you actually look back at 2019, that's just about 2 years back, 3 years back, there was a Nobel Prize given which was basically given to Michel Mayor and Didier Queloz, basically for their discovery of the first exoplanet around a sun-like star, right? And if you actually see in this was way back in 1995 when Didier was just a student, a PhD student of Michel Mayor, and they were working in Geneva University, and that's when they discovered a planet around the system, 51 Peg B, that's the planet. Now, the idea that exoplanets exist and life exists outside our, other than our planet is an old idea. So one of the earliest ones we have is the words of Giordano Bruno, who actually said the space we declare to be infinite, in that there are an infinity of the worlds of the same kind as our own. But at that time, obviously, the church was not very appreciative of Bruno's words, and Bruno's was actually punished. He was burnt alive for this statement of his, because it was believed that the universe has just been created for man, and there's no other place in this universe for anybody else. And then there were various methods to which people actually tried to look for exoplanets. And searches went on for many decades, for many teams, many stars, many different techniques. And but it was without success. So so the question was, were the techniques not sensitive enough, or is it that there were no planets? And it was really confusing as to, is it really worth it looking for alien life? But the first possible evidence of an exoplanet was noted. The first confirmation of the detection was in 1992. I'm sorry, this seems to have gone. And as of January 2022, this is an older one, we have more than 4,000, 5,000. But today, I told you September, there are more than 5,000 confirmed exoplanets. Now, what's it about the detection techniques? How do you actually detect exoplanets? Now, you know that looking for it is literally like looking for a needle in a haystack. There are various methods. I will cover those methods. There's a method called the transit method, which essentially means that you have the star, and if the exoplanet comes in front of us, it transits, you will actually find a fall in the brightness. And that's the transit method. It can be done from space. It can be done from ground-based telescopes. And that is the bulk of the, method of actually detecting exoplanets is the transit method. But there's another very popular method, which is the radial velocity method, which is the method which was done by Didier Queloz, for which they got their, Michel Mayor, for which they got their Nobel Prize. That was using the radial velocity technique. And then there are some other techniques through which also you can actually look for exoplanets. So like I mentioned, these are the four techniques. One is the radial velocity technique. That supposing if you have a star and you have a planet going around it, then if you were looking at the spectrum of the star, there would be a time when, depending upon if the star and the planet were going around each other, right, you will be having a time when the star is coming towards you, when it is what is called blue shifted. That means that the spectral line, which should be at a particular wavelength, it gets actually at a shorter wavelength, which is called blue shifting. And when the star is going away from you, it gets red shifted. That means it moves to longer wavelengths. So in this, you can identify the motion of the star, and you basically just apply the formula for Doppler effect, that delta lambda by lambda is equal to V by C. And with that, you can get the velocity of the star. This is the radial velocity technique, which was applied by Michel Mayor and team. The other method which I spoke to, which is more prevalent, which actually has given us much more results, is what is called transit photometry. This is the star, and the planet as it comes in front of the star, there is a fall in the brightness of the star, and that's what you call transit photometry. There's also another technique called microlensing, that there is a lensing effect caused because of the presence of a planet. This is much more difficult to detect. And then there is direct imaging, that supposing you have a star and you have something called a coronosphere, you can actually, cover it's like in an eclipse. You cover the star in some way. That's when you can actually see the planets. So these are the most standard, most popular techniques of actually looking for them. So there's an animation over here. You can see the radial velocity technique. This is the star. This is the planet. They're both going around their common center of mass. And because of that, let's assume you cannot see the planet because the planet is faint. It's not giving out much of light. But you will definitely see a wobble in the star's position, right? And similarly, you are also going to see this wobble in its velocity. Velocity in the sense, the velocity suddenly it's moving towards you and away from you. So there's a certain amount of spectral shift, right? And that's what you're going to see in this case. And based on that, you can actually get the period of the thing and you can actually detect it. Like I mentioned, this is how you'd actually look at the radial velocity technique. Here's the star and here's the planet, right? And if you had a spectral line, so you can look at these dotted lines is the wavelength of the spectral line without any shifting. But as the star is moving towards you and away from you, so you can see that when it's moving away from you, it moves towards the redder star, redder region. And when it's moving towards you, it moves towards the bluer region. And therefore, there's a shift in the wavelength of the star, the light emitted from the star. And this shift, delta lambda by lambda, gives you your V by C value. So as the velocity of this star, you can see is moving towards you and away from you, you are basically going to get it on this. So if you're looking at it from here, if you look at it from here, you would see it looking something like this, where the star is going like this. And as the speed varies, you will see this red shift towards the right-hand side and blue shift towards the left-hand side as the star moves, right? The radial velocity technique, which I mentioned to you earlier, was the technique used by the Geneva team. That is this thing where you're actually going to see this Doppler shift. Now, obviously, the Doppler shift that you can measure is a very precise value which you've got to get of the delta lambda, which obviously depends upon the precision with which you can actually measure, right? So actually, it obviously depends upon the distance of the observer. So if you observe Jupiter, Jupiter causes a variation of about 13 meters per second in the motion of the sun. The Earth gives only a difference of about 0.1 meters per second because the Earth is less massive. And therefore, if you were, for example, using, this is one of the best spectroscopic instruments, the HARPS instrument at the ESO. This is the European Space Agency, Space Astronomy, Space Southern Observatory, 3.6 meter telescope. This measures up to a limit of about 1 meters per second. So a Jupiter-like planet can be measured using this instrument. But for example, an Earth-like planet cannot be measured because the measurement should be it's about 10 times more precise. So if you were looking at if our solar system itself using this instrument, you would probably be able to detect the presence of Jupiter, but you won't be able to detect the presence of the Earth, right? Now, another important thing when you're looking at exosolar planets is the tilt, right? And in principle, you will not know the tilt of the system for you to know at whether you're looking at the system from here or from which angle, right? The Doppler shift only tells you the velocity, projected velocity, right? Along your line of sight, it tells you the projected velocity. But in principle, that is just the projected velocity, which is m sine I. So if the system is inclined to us at an inclination of I, right, which you're seeing it like this. For example, if the system is going around like this, right, where your inclination is equal to 0, right? In that case, what happens is the planet is going around like this around the star, right? You will not get a Doppler effect because at all points, the planet has the same distance from you. It's not moving away from you. So therefore, if it's m sine I, you will not see it. It will be equal to 0. But if, for example, if your eye is equal to 90 degrees, you're seeing it like this, right? In that case, you're going to get the maximum effect of this projected velocity, right? So we always need to keep it in mind that there's always going to be an error in our measurement because we do not know the value of the inclination of the orbit. Now we'll get back to Didier Colletz and Michel Mayor, where I showed you how did the field develop. So like I mentioned that if you actually were looking at from a distance of about 5 astronomical units, an astronomical unit is 150 million kilometers. 150 million kilometers is the distance between the sun and the earth. If you were to go at a distance of 5 times larger than that, right? Then, for example, if you were to see the tug of Jupiter, it would create a wobble of about this much. So the wavelength shift would be about 10 power minus 5 nanometers in visible light. So this delta lambda, which you see in this formula over here, delta lambda by lambda in the formula, which you can see over here, that delta lambda is that small. It's only 10 power minus 5, right? So that is the kind of precision you require for your telescope to have or your spectroscopy instrument so that you can measure this kind of a difference, right? So the first confirmation which was made by this team was in 1995, where they measured a giant planet with a 4-day orbit around the star 51 Pegasi, right? And like I mentioned in this case, this was a giant planet, because giant planets are much more easier to detect. The wobble they create is much more larger. So if the system has a low mass planet, it could have another planet in the system which has a lower mass. That will be more difficult to detect, like I showed you, because, for example, the tug that the Earth creates is much lesser, so it would be more difficult to detect. So there is a certain bias in your observations, that you will observe the more massive planets which cause the larger, shift. Now, in the case of 51 Peg, it is a Jupiter-like planet, but it's a hot Jupiter. Why is it a hot Jupiter? Because it's about 7 times closer to its star than Mercury is to our sun, right? Even the example we are going to do today also, we'll do an example in which we'll see that this planet is really very close. It's about 0.04 astronomical units, right? It's much closer to its parent planet compared to, for example, the Earth. And therefore, when this was detected, these people thought, the team thought, that there's something wrong in their detection, for the simple reason that this was such a big planet. It was a Jupiter-like planet, but it was very close to its star. So they thought that how could such a big giant actually form so close to its star? Because the star is hot, it's sending out some kind of hot air, hot radiation, and for you to form such a large planet so close to it would be difficult. And therefore, initially they actually suspect what is called planetary migration. In the sense, when we even look at our own solar system, there are reasons we believe that the planets must have formed at some other locations than where they are just now. For the simple reason that, we come to that a little later. There are theories of planetary migration, right? And so studies of like this actually give you a good insight even to the understanding of our own solar system, right? So it's possible that this planet actually migrated, it formed somewhere else, and then it came closer to its star. But it seems to have lost some of its atmosphere due to this high temperature of the star at this thing, right? So, like I mentioned, is there already exists a theory called the NASI theory, which is actually a theory of planetary migration, where there is reason for us to believe that the planets of our solar system formed at other locations, but they later on moved away from their original location. And possibly the 51 Peg example is also an example of a planet like this, where the planet seems to have formed somewhere else, and then for some reason it has come closer to its star, because such a planet could not have formed so far from its star, right? So, like I said, studies like this help us even revise our own ideas of star formation, solar system formation of our this thing, right? So until around 2012, the radial velocity method, which we just had a look at, was the most popular method used to look for exoplanets, right? And then after 2012, there was a space mission, which we'll talk about in a minute. It's called Kepler, and Kepler was launched. And that's when Kepler actually used the transit method. And that's when suddenly there was a big boom of a large number of exoplanets which were discovered using Kepler. Now, in this case, you see that you need a high signal to noise ratio in the spectrum to actually detect the radial velocity, this thing. So we'll actually come to it and we'll see that how do we actually detect it and what are the problems. So the radial velocity method, one problem could be is that you could have multiple planet and multiple star systems, due to which you could have a wobble, right? Similarly, you could also have a shift in the spectral lines because of magnetic fields, as well as certain types of stellar activity, which can also give false systems. And therefore, to confirm that the radial velocity shift or the spectral shift is happening because of the presence of a planet is a little difficult. And therefore, plus you do not know the inclination, so you don't know the m sin. You're only measuring m sin I. You're only seeing the projection of the velocities, and therefore those were the problems with the radial velocity technique. However, the transit method it was a good one in which you could actually rule out false positives, position of the planet. And therefore, like we'd see, the transit method got a bit more popular. So like I mentioned earlier, the transit method is the one in which the planet comes in front of the star, and then the brightness from the star actually drops. And that drop is what you need to measure, right? That's what is called the transit method. What you need to note is that, for example, if we take a star over here, right? And if you take a G2 star, which is approximately a star like the sun, and if you have a planet, right, coming in front of it. So for example, if we were to just take the Sun-Earth system and we take a ratio of, obviously the difference in the brightness will be the ratio of the area which is covered by the planet compared to the area of the star. So it would be pi r star squared divided by pi r of the planet squared, right? And here you can see that if you substitute the values, for example, r squared by r squared for the sun and the earth, you'll see that the ratio is about 10 power 4 times. So it's 1 in 1000 is the value which you're going to get at which you'll have this. So the depth, this depth of this, like I said, is the ratio of the square of the radii. And therefore, if I want to get the radius of the planet, it would be radius of the star into the root of the ratio, right? And typically, for example, obviously the star is much, much larger than the planet, and therefore this would be very difficult. So if you have 1/10,000, right? So it's like having 10,000 bulbs on and only one bulb gets switched off, you need to detect that, right? That's the precision with which you need to do it. So Kepler actually does that. It actually looks at stars and sees the difference in their brightness. But note in this, you can see that if the brightness it is scaled here for 1, you can see that the dip which you're getting, this is for hat P7b, you'll see that the dip you're getting is 0.994, right? So it's 0.006, right, is the ratio, right? So it's about 0.6% is the ratio of the fall. So obviously getting this fall is very, very difficult. But the standard norm is that, so often the dip is like 1% or even lesser than that. But typically to confirm it, what people do is you need to catch at least 3 transits, right, to get the, but once you get that, we can see today how with that you can find out the size of the planets. You can even get the number of planets depending on the number of dips you're getting. Then with this, you can also get the period, right? And you can but obviously to keep in mind the inclination effect. So this is similarly, people can also observe exoplanets using over here. You see, this is a small telescope. It's just a 16-inch telescope with which people try to observe the exoplanet around the star WASP-33b. And you can see that when they observe this thing, you're getting this dip with a 16-inch telescope. But again, you can see that in astronomy, we have a scale of brightness called magnitude scale. So this is a star which has a brightness of about 12.2 magnitudes. And here you can see that the dip is coming in 100th of a magnitude, right? So that is the kind of precision you need to do in your measurements of what is called photometry, or the brightness of the source, so that you can actually get this dip, right? This dip, please notice the numbers over here. It's very, very small, okay? The other method which is used is what is called microlensing. That suppose if you're looking at a star and there's a planet coming in between, you know that gravity can bend light, right? And that is what is called gravlensing, right? Where gravity behaves like a lens, it bends light and gives you this bent light effect. And therefore, for example, if I have a star over here and a planet coming in the front, the light gets bent, and therefore when the observer observes it, you see a lensed effect. And what is this lensed effect? That if you actually see the light curve, you'll actually get a bump. So you can see that over here. This is the star with the planet, and you have the light over here, and you'll get a bump like this which comes because of the microlensing effect. So I have a faraway star behind, and then as the star and the planet come in front of it, it'll have this. But obviously detecting something like this is very, very difficult, because you need to have this ideal placement where you have a star in the background, and then you have this other star and planet which comes in the front, and they cause this effect to come, right? And therefore, it's not a very easy thing to detect the microlensing effect. Again, here you can see an animation of the microlensing effect, that if this is happening with the lens effect, because it behaves like a lens, you'll have a sudden rise in the brightness, which you're going to have because of this microlensing effect coming, right? The other method which is used is called the direct imaging method. So like I told you, again, this is very, very difficult to see because the star is very bright compared to its planet. And therefore, if you were even looking at the Jupiter and Sun thing at a distance of 5 parsecs away, which is a large enough distance, the angular separation of Jupiter and Sun will be very small. This is less than 1 arc second. This is a measurement in astronomy. But in short, it will be very, very close by. That separating this would be very, very difficult to cut off this light and actually to get this thing, right? And this works out very well if planets have wide orbits, in the sense the planet is, reasonably far away from the star, so that I can cover the star and I can see the planet. And you can see it like this. So here you see an example of a star where you cover the light from the star, and then you can directly get the 3 planets, that is B, C, and D, right? So what is done is, if this is 51 peg, 51 peg A is the star, and then B onwards, you name it all for the planetary systems. So this would be the planet, the first planet, the second one, and the third one for the system. Now, like I told you, the biggest problem in direct imaging is that because the star is very, very bright, the planet is not so bright, so you cannot see it. So what is the way out of the problem? So the way out is what is called a coronograph, which in principle is like creating an eclipse. You'll all know that when we have a solar eclipse, if you cover the disk of the sun, you can see the outer regions of the sun, which is called the corona. The corona has a brightness of about 1,000,000 kilometers. So you can see it over here. But over here, what happens is you artificially cover the light, putting something called a coronograph. And therefore here, this is an image of Saturn where you can see it's covered, but you can see its moons, right? And this is another image. This is an image of the sun itself. There's a spacecraft called SOHO, which is out in space, which is, observing the sun, measuring its brightness. And here what you have is you cover if you cover the sun artificially using this coronograph, you can see the things on the outer part of the sun. So you can see that these are flares, and there are various features which are there in the outer parts of the sun, which you can see if you cover the disk of the sun, right? So here, for example, you can see this thing where you can see this video should come on. Yeah, you can see over here, when I cover the star, you'll then be able to see the planet because the star has got covered. Otherwise, you do not see the planet. The planet is sitting over here. You do not see it because the star is so very bright. But if through some means, it could be naturally, there's what is called an occultation, or it could be that artificially you actually get this coronograph, which covers the star, then you'll be able to see the planet, right? So direct imaging technique is also used in a whole lot of telescopes where you actually do this direct imaging by use what is called a coronograph, right? So it has been used, this is the very, very large telescope in which it's been done. This is the Hubble Space Telescope where it was done. And this is a Keck image, which you can actually see it. So you can actually see it. And with this, you can actually image extrasolar planets, right? So this is another system where you can cover the star and B, C, D are the planets around it. Beta Pictoris is also a very interesting system, which has its planetary system. And here what happens is if you put a coronograph around this, you can actually find this is the location of the star and B is the first planet, right? Like I told you, Beta Pictoris A will be the star and Beta Pictoris B will be the planet over here, which you can see over here, right? Now we come to the Kepler mission, which we are going to focus on about today. And it was realized, like I told you, when you measure the brightness of these stars, it needs to be measured with a very good accuracy. But the problem is if you're on the Earth, there is the atmosphere, and the atmosphere has turbulence. The atmosphere has various effects due to which you can have a fall in brightness, right? Which could be not due to the presence of the planet, but because of some other feature, right? And therefore, the safest thing is to go and observe things from space. Because in space, you don't have any disturbance because of the atmosphere. You can continuously look at your object. You can monitor. There's no problem about sunrise and sunset. You can observe 24/7. And your space is stable, right? So the photometry that you're going to measure will be very, very accurate. So the Kepler mission was launched in 2009. It has a size of about 1.4 meters. And what it did is it basically studied only one part of the sky, which has a field of view of about 115 square degrees, which is approximately 0.25% of the star. It's like, if you put your fist at arm's length, that's the kind of area it's going to be observing, right? So they selected a region in which it's out of the ecliptic plane, and it's in the Cygnus and Lyra constellations of our galaxy. So after some time, after Kepler was launched, 4 reaction wheels on Kepler actually failed. And therefore, then Kepler could not do what it was actually originally planned to do. And therefore, a slight change was made to the program for Kepler. And it was then called the K2, which is Kepler in the second phase with that problem. And with the problem, they still continued getting observations of a slightly different kind. And which are obtained with the K2 mission. So you will find Kepler and you'll find K2. K2 is the subsequent ones. And then Kepler is now, it's a bit too old. And therefore, in 2018, another mission was sent, which is called the TESS mission. And this is an exoplanet survey satellite. Now, let me let you know that in astronomy, there's a lot of data now available. Astronomy has now become a very data-rich science. And typically, these satellites, when they're monitoring the sky, if you look at Kepler, when it's looking at this sky, it's looking at a very, very large number of stars. And for these very large number of stars, there are light curves which are constantly coming out for these stars. And obviously, the number of astronomers are not sufficient for the amount of work that needs to be done. And therefore, what is done is not only even for the Hubble Space Telescope or even Kepler, TESS, K2, etc., all their data is available online, right, at a certain website. I'll show you the website. And people can access it, analyze it, and study exoplanets, right? So it's actually open out for people to use. And that's what I'm going to show you today of how you can actually use the Kepler data, which is available online, to actually analyze and get exoplanet parameters. So for example, just as an incentive to you, here you have an example of, this was pre-COVID in 2020, where actually a whole bunch of students, right, here, using Kepler data, you had a PhD student called Michelle Codimito, who actually discovered evidence of So you could have students like y'all. This is an incentive to y'all, where y'all can actually discover new exoplanets using the data that's available, right? So similarly, there was an older paper also where radio emission was also used to study this thing, but we won't talk about radio much today. So there are various exoplanet missions, and of which I spoke about Kepler and TESS. These are also 2 other space missions, which is called Spitzer and Hubble. And other than that, there are a whole bunch of exoplanet missions, which were specially designed to look for, for extrasolar planets, which include Kepler, TESS, Spitzer Hubble partially looks for exoplanet, but Kepler and TESS, 100% they only look for exoplanets. Webb, which you all must have heard about, James Webb, is also looking for exoplanets, other than the agenda it has, right? So it does look at other things too, but it's also looking for this thing. Now, planets can be of various kinds. They can be gas giants. They can be Neptune-like ones. They can be rocky ones like the Earth, or they could be super Earths, which are potentially rocky but larger than the Earth. So let us see what are the typical kind of exoplanets that we have found. You already know now, thanks to Kepler, thanks to TESS, thanks to radial velocity measurements, we have a very large data set of exoplanets. So you can see that the different colors have been used to describe the method used to find them. And like I mentioned, these techniques also depend upon the kind of object you're looking for. So radial velocity very easily can find ocean worlds, ice giants, because basically it's looking for a wobble, right? So you need a nice massive object which can actually do it, right? And typically for a period of within about 100 days, right? But for example, transits are measured like this. So if you're looking with Kepler, typically these are objects which have lesser orbital periods of about less than 10 days, right? You could also do it with the other methods, for example, using, we won't talk about those today, but there could be imaging also, which you can do today. Do to look for exosolar planets. You can do other methods also for it. The rocky planets, which are the Kepler ones, you'll get it through this, right? Okay. Now, typically, so if you actually see this previous one, the distribution, this is the size relative to the Earth. So you see that there are obviously more number of them larger than the Earth. Similarly, even orbital periods, we can see these ones, and obviously there's a path bias because of the techniques we are using to observe them. Therefore, we see only certain periods. We do not see these large periods because we are not monitoring at that scale, right? We are not monitoring at the scale of 1,000 days. We are monitoring at a lesser scale. If you also look in terms of planet this thing, you can see, like I said, we are basically observing planets which have periods less than 10 days, less than 100 days, right? As well as which have radii. There are a good amount of them which are close to the Earth radius, but also a large number of them which are larger, right? So this is called a discovery space. So typically Kepler, right? Kepler looks for planets with orbital periods less than about 400 days, which you can see in yellow over here. And the yellow and red dots show planets basically by transits. Blue dots is radial velocities, and Kepler is with yellow, right? So here also there's a description of the kind of extrasolar planets we see, and those you can see over here. So if you look in terms of planet size, you have, these are the sizes which are not seen in our solar system. We don't see these types, but these are the types which you can see. So the most common planet sizes are those with radii which are about 1 to 3 times that of the Earth. That's the most common type which you can see, that we call Earth, super Earths. These are the typical kind of planets we can see. Again, the bias is partially because of our detection, right? Now, another interesting thing is to see the mass-radius relationship, because the mass-radius relationship in principle is a function of density, right? Density is mass upon radius cube. And therefore, if you actually look at mass-radius, these actually are a study of the kind of densities you have of the extrasolar planets. And therefore, what you can see is that if you had this range, the red one, these are typically for magnesium silicon oxide, which you'll see over here. But these are the kind of densities you have for these. And these are the exoplanets which have densities which are of this kind, right? Which basically sit in this kind, right? But if you want iron, for example, iron exoplanets, they are the ones which are lower down over here, right? These are with high densities. So mass radius relationship is of this kind. Typically, if I were to actually see periods in terms of radii, you will see, like I said, these clumps which you see, partially it's because of the method of detection, and partially it's because of the actual content, right? So if you actually see, if you were seeing in terms of massive, we see a good amount of massive planets which have lesser periods, or these ones, while you have these objects also sitting over here. So if you want to actually estimate the number of Earth-sized planets in our galaxy, we can see that our galaxy has about 400 billion stars, and about 100 billion stars of our galaxy belong to a spectral type which is called FGK, which is about similar stars to the stars like our sun. And therefore, if about 100 billion stars are similar to the sun in our galaxy, we'd say about 1/3 of them actually have Earth-sized planets. And therefore, in principle, if you were to make an estimate, there's also a famous equation called Drake equation, which we are not doing. But here we are just estimating the number of Earth-sized planets. And so typically we say that if 1/3 of these sun-like stars have Earth-like planets, then if you were to actually say 300, you'd get about 30 billion Earth-sized planets in our this thing. And probably if you include the super Earths, you get 100 billion. And therefore, definitely it's a very good idea to look for planets within our galaxy itself. And so we are already discovering a very large number of planets which are of the Earth size. And they are obviously amongst the most important discoveries in modern astronomy. Because first of all, the step is you look for Earth-like planets, and then you're going to look for habitability and other indicators of life, right? So there are some more examples, but in our solar system, what we see, our solar system planets, typically our solar system planets are some ones which lie in this region. These are not the kind of planets which we are finding. We are finding the bulk of planets like this or like this, which are of these kinds, but our solar system-like planets are not what we find. They actually occupy this region of space, which have this kind of periods, right? We have the periods is in hundreds of days, right? For example, the Earth, 365 days. So you'll have it sitting somewhere over here with a radius of this kind, 10 power 0, which is 1. And therefore, our solar system, or the Earth is occupying this space. So finding Earth-like planets is still a little difficult. If we actually look at the orbits of extrasolar planets, you can see that if you were to actually plot average orbital distance versus eccentricity, you will see that all our solar planets, they are approximately like this. Eccentricity is very low. Eccentricity is telling you how does it differ from a circular orbit. So if you have 0 eccentricity, that is about a circular orbit. So you can see that our solar system planets have near circular orbits, but the ones that we are finding, the extrasolar planets we find, seem to have much larger eccentricities. Obviously, again, these are the ones which are easier to detect, right? More easily available to detect. These ones are lesser. We are essentially finding these kinds and not the kind that we have, right? So if you were to actually plot orbits of extrasolar planets, most of the detected planets, they have orbits smaller than Jupiter. They are closer to their stars. And that's basically because planets at greater distances are harder to detect using the Doppler technique, because obviously their gravitational tug will be not so strong, right? And therefore what we are detecting is massive planets which are closer to their star, right? Like the one which the Geneva team did. It's a Jupiter-like planet closer to its star, because such a planet is obviously going to cause a bigger wobble, right? And therefore it'll be easier to detect. So like I said, most of the extrasolar planets we have seem to have elongated orbits, larger eccentricity than the ones of our solar system. Similarly, some stars have more than one detected planet, but if you actually were to see how many of them have multiple planet systems, so you can actually see, if you look at this, for the number of ones which have multiple planet systems, right? So you can actually plot them and see what are they like. Similarly, if you were to look for the masses of extrasolar planets, again, because of our detection techniques, we obviously have a peak coming over here where you're obviously seeing it for more massive ones. This is the one for our solar system, but you can see that the thing is coming something like this, right? So hot Jupiters, like we mentioned earlier, these are Jupiter-like stars, planets, which are very close to their home stars, right? So this is an earlier slide, which is not updated as yet. But of the 3,700 confirmed exoplanets, what you can see, the bulk of them, like I said, are Jupiter-like, Neptune-like. These are the bulk, what are giants. And again, like I told you, that's basically because of our detection techniques. But the lesser ones are the Terra-like, the Earth-like, which are over here. And the Earth-sized ones are about 700 out of 3,700. And Mercury size is only 5. Again, this is, like I said, this is, in astronomy, we always have to be very careful about the bias which we get because of our observation techniques. So if we are observing more hot Jupiters, that does not mean that hot Jupiters are so abundant in the universe. It's just that in our detection techniques, we are detecting them much more, right? So as of today, this is an older date. As per this, this is an older date, so I will skip this thing. And now that we know how to detect them, right, we spoke about the detection techniques. How many exoplanets do we expect to find now that we're actually looking for it? And why do we expect to find? So I need to just speak a little bit about this, is that let us go back to our solar system, right? How did the solar nebula, how did the solar system form? So what is the present understanding of star formation? That when stars form, they basically form from a molecular cloud where, because of gravitational collapse, the material collapses and you have a star forming in the center. And the outer region, which is the debris disk, etc., that's where you have planets forming, right? So typically, like I said, stars, there's a giant molecular clouds like this, which are cold and they are dense. And in such a cloud, what happens? You basically have two forces. One is the gravitational force, which is pushing it in. The other one is the gas pressure, which is outwards. If it's a low mass cloud, then the gravity is not so strong. the gas pressure is much larger and therefore the cloud sustains like that. But if, for example, you have a high mass cloud, in that case, what happens is that the gravitational force dominates over the gas pressure and the cloud actually collapses in its own weight, right? And that's exactly how stars are formed. So what happens is, as this big cloud, let us assume we have a cloud which is so massive that gravity dominates, this thing collapses. And as it's collapsing, what happens is, because of angular momentum, you have a disk forming around it, right? And within this disk, when you have clumps, these clumps are where actually planets form. So therefore, this is the typical thing which you would see for star formation. You have a dark cloud which collapses at its own weight. It forms a disk around them. You could have some outflows coming out, and then gradually from this disk, you have planets forming as this material accretes. And therefore, with our present understanding of star formation, we know that planets form along with stars. We also have observational evidence. So this is a Hubble Space Telescope data of very, very young stars. And you can see these very young stars which have disks around them. And these disks are where planets form. So this is again Hubble Space HST data from Orion Nebula, which is a star forming region, where you can have these disks where you can have planets forming. And here you have even more newer data. This is using a telescope called the ALMA. This is a sub-millimeter telescope. And we actually have images. This is a very young star where you actually have a protoplanetary disk around it, where you can see, these regions forming. And within these regions, you have planets forming, right? So this is a real image. And ALMA has actually given us images of loads of such systems where you have planetary systems forming around very young stars. So you can see that in principle, with our present understanding of star formation, you can see that planetary formation is actually a byproduct of star formation. So in principle, when stars form, planets form along with them. The only difference being that if the star is a bit too hot, right, if there's too much of radiation coming out from it, then planets probably would have a problem in forming. But if most stars are not so massive, which we know is true, then the planets can actually form. So therefore, as per that understanding, planets should be common. And almost every star should have one or more planets because the number of massive stars in the universe is very less. Most of the stars are low mass stars. And therefore, those kind of stars will form planets. So what's our goal? Our ultimate plan is, first of all, to find exoplanets. Second thing is we can look for habitability. If we know the properties of the star, we can know how does the temperature change from distance from the star, right? Once we check on habitability, you can also do spectroscopy, which is you actually take spectrum of the star or the planet to actually then look for signatures of life, right? So you actually look for the spectrum, you see what are the molecules you're actually getting in that. Based on that, you could see that. And then finally, the idea would be of actually contacting. So if you were to actually look at the sun's closest neighbor, this is the sun at a distance of about 100 AU. We have what is called the Oort's cloud. And then you have the closest stars to us. There's Proxima Centauri, which is basically a binary system, a double binary system. And there's Bernard star also. And there are various closest neighbors of ours. Now, if you were to actually, even for the sun, if you were to look for the habitable region, you know that if you're too close to the sun, for example, Mercury, it's too hot. If you're too away from it, it's too cold, like Jupiter. While the Earth is actually called just right, where you can have liquid water in liquid form. That's the habitable zone. And this is also called the Goldilocks zone because this is the zone where everything is just right. Most of you all will remember the Goldilocks story of the soup being too hot or the soup being too cold. And Goldilocks finally has the soup which is just right. So this is also called the Goldilocks zone for a star, looking for the region where water is in liquid form, where the conditions are just right for life, the habitability. And therefore, for example, for stars, depending upon the distance of the star, you can actually find the habitable zone. So therefore, for various extrasolar planets, we can actually calculate, like I said, the habitability zone, the zone where water is in liquid form. And you can actually look for which of these exoplanets actually fall within their habitability zone. So this is the Earth. Venus and Mars, you can see, are just on the edges of habitability. That is why they're the two planets where we actually look for life. And similarly, there are a whole set of other exoplanets also which seem to be in the habitability zone of their parent stars. So these are the interesting ones, which are the ones to look for. Some of you all may have heard about the Trappist system. This is a system which is made up of, like I said, A is the star, B, C, D, E, F, G, H. And these guys are all, the system around that. The inner solar system also, if we were to see, these three are within the habitability zone, the green part. And like I told you, for our solar system also, Earth is habitability, obviously, and Venus and Mars are the edges, right? So they actually are the interesting systems for us to see. So if you actually see in this thing, the Trappist system, okay, I've not plotted it over here, but it's one of the closer ones, which seems to have planets within habitability zone, which makes them very interesting. So there are a whole set of potentially habitable exoplanets which we have, and you can see that over here, which are there for exploration. But I would also like to conclude very soon with something very simple. Often people have this feeling that, the human beings, we have actually messed up with our own home planet, right? There's global warming taking place. There's so many problems which are on our planet. And I would like to clear a doubt, which often people think that we are looking for exoplanets basically because we are looking for another home, right? But I would like to quote the words of Michel Mayor, who actually says that we'll never colonize exoplanets. That's a bit of a strong statement. We may probably colonize them sometime. But the idea that looking for exoplanets is basically to look for an alternative home is obviously something very, very far-fetched. It would be very difficult for us to actually find a habitable home in these exoplanets to actually go and live in, because we are messing up the earth. It is definitely a much more easier option for us to undo the problems which we've caused on the earth, right? Rather than look for another earth, because it's a very difficult thing to find exoplanets, find earth-like planets, find habitability and conditions is something very, very very difficult. So I would say that maybe this statement is a bit too strong, where Michel Mayor says that we'll never colonize exoplanets. But I would like to say that you should be clear that we are not looking for exoplanets because we are looking for alternate homes. We are looking for exoplanets because we are looking for alternate life. We are trying to understand our own solar system, trying to understand formation of life, origin of life on our own system. And that's what we're trying to understand, right? And therefore, I will conclude that this is a picture, very well-known picture, which is called the pale blue dot. And these are, again, words of Carl Sagan, which I started with, which I'll end with again. That over here, which you can't even see in this image. This is an image which was taken by Voyager, the Voyager mission. And this is an image of the Earth from a distance. And look at this dot. That's here, that's home, that's us. And basically, that's what Carl Sagan was saying, that the Earth is definitely a very unique planet, habitable for us, and that is home for us. And we basically need to do our best to, conserve it. So I'll wind up with this, with a few takeaways, that very likely that all stars, and nearly all stars rather, should have planets based on our current detection rates, as well as our understanding of star and planet formation. As per that, it's very likely that there are a large number of this thing. And at least a few percentage of systems with planets, and likely more, actually have Earth-like planets. The worst case scenario would be at least tens of millions of Earth-like planets do exist in our galaxy. And therefore, various space-based exoplanet missions like Kepler, there's Carrot, as well as ground-based spectrographs, like, for example, HARPS, WASP, HIRES, GELT, all these are spectrographic spectrometers on very large telescopes. They actually show us that exoplanets are there everywhere. There are a large number of hot Jupiters, big planets further out, water worlds, super Earths. Some of them are rogue planets which are away. Some of them with highly eccentric orbits. There are systems which are like Tatooine, which we saw, planets in binary star systems which are common. And there are a whole lot of discoveries which are taking place in this. in the next session, I'll even show you the data which James Webb got on exoplanets. And therefore, this is a very rapidly changing field. There's a lot available on the net, and you will find a lot of information about exoplanets because, like I said, this is probably one of the most rapidly changing fields in astronomy where a revolution is actually taking place. And you are witness to that revolution which is actually taking place. So there's some nice pictures also on the NASA website where you actually have travel posters for travel to various planetary system based on the information we now have with our data about the conditions on these planets. So I'll wind up with that. Thank you very much. And these are words of Asimov, which earlier at some time people probably thought the study of exoplanets is something which is, science fiction types, which is something very much in the future. But I think the future is over here, and today's science fiction is definitely tomorrow's science fact. So we look forward to a very interesting future, which we will have with new studies of exoplanets which are taking place. So thanks a lot, and I'd be open for questions now. Thank you.
Thank you, Dr. Priya, for such an exciting and informative talk, which will definitely pave way for students to take up this field in future also. And the house is open for questions. We already have 2 questions which are there in the chat. So I'm reading it from Vishwanath Mali. What are the various methods to scale habitability of exoplanets?
1 second here. What are the, could you just repeat the question?
What are the various methods to scale habitability of exoplanets?
Okay. So like I said, one of the standard methods is looking for where do you have water in. I think I should stop sharing, right? Can you just stop my share? Yeah, okay, I'll stop sharing. Yeah. So one of the most standard things which is used is to look for a planet where you have water in liquid form, right? Or what people do is, that the temperature falls as you're going from the distance, right? There is Stephen Boltzmann's law, right? Luminosity is equal to 4 pi r squared T power 4. And therefore, you can find out the temperature. So often people, either they look for temperatures as with waters in liquid form, 0 to 100 degrees. And that's a typical thing. So it's done with temperature when you're looking for habitable zone.
Right.
Now, if you want a more detailed thing, that is what we hope to now get with James Webb, is where you actually then do spectroscopy, right? You get spectroscopy, then you will get the chemistry of that place. So then you will know what are the chemical elements present over there, right? And could they be the kind that could be caused by life or which can sustain life, right? Even life on Earth, or it could have any form of other life. So the next step is spectroscopy. The first step is temperature, and temperature I will show you in the demo today where using Kepler data itself, we know the temperature, you can find the habitability zone. But the next step is spectroscopy to actually get the chemistry of that place to see what's available, right? Yeah.
I hope the question is answered for Mr. Mali. Next question is by Mohammed Asif. This side, he's saying he's from Kashmir and he's complimenting to you for a wonderful talk. And his question is about recently discovered exoplanet HIP 65426b by JWST. And he's asking to share your thoughts on that, how the JWST can find exoplanets like Earth.
Yeah, so one of the key aims of JWST is to actually look for exoplanets, right? Because what happens is, the problem is, like I told you, that exoplanets do not emit their own light. They reflect light of the star. And the problem is that because of that, and then they are small in size. And therefore, so if you want to observe an exoplanet, you need a really big telescope. And again, the problem is, on the Earth, you have the atmosphere, which actually, smudges things, spoils something which is like called seeing. And therefore, James Webb is a 6.5-meter telescope out in space, right? And I'm sure you'll have seen some of the images. So it is obviously expected. So JWST is just, if you see the first images which were out from JWST, I'll show that to you in the next session. You already saw that they could very well detect water, right? I hope you all have seen that image of JWST showing water. And therefore, very big change is supposed to come. And part of this naming exoplanet thing we are going to talk about is basically all of them are target exoplanets for JWST. So JWST is going to do the job of doing spectroscopy for all these exoplanets. And JWST can possibly find an exoplanet like us. We really don't know. We are expecting something interesting. Yeah.
Yeah, thank you so much. I think Venus is an exception to that habitability because, in spite of being in the habitable zone, its temperature, because of the climate change and because of the greenhouse gases, is quite high. So that isolation is very difficult to do for exoplanets.
No. But you may be aware that, there was the time when they detected phosphine
Yeah,
on Venus, right? A few
that's
years
right.
back, and there was so much of noise about it. And even till now, in the scientific community, the thing is that Venus is hot, yes, but then Venus has clouds, and
Yeah.
on the clouds, there's a whole range of temperatures. And there is a part which has a temperature which we consider as, liquid water, which is habitable. So a part of the clouds of Venus are habitable, not the surface. The surface is very hot, 400 degrees Celsius.
Mhm.
But if you go above, then you have it in the clouds. And the detection of phosphine was in the clouds. And
Yeah.
therefore, there is a whole set of, the phosphine people, as well as there's a whole set of people who are actually considering life in Venus in the clouds. And therefore, you may be aware that there are about some 5, 6 missions which are
Mhm.
planned to go to Venus to actually check it out. Even in India, ISRO is doing a Shukrayan mission, which is just to go to Venus and check it out, right, to sample it. Similarly, there is what is called, NASA has a Veritas mission, there's a Da Vinci mission, even MIT is doing another mission, Life Finder mission. So there are at least some 6, 7 missions which have been planned in the next 10 years, which are only for Venus. So Venus life is not yet ruled out. We are still
Yeah.
checking.
So,
Yeah.
but it is very difficult to isolate the effects of greenhouse gases, like they are causing this rise in temperature in spite of being in the habitable zone. So
Yes,
that
but
may
the
be there
problem,
on the exoplanets also.
yeah, so actually, see, one problem with looking for life is we think is life is what we think it is, right? Carbon-based life, the kind of life that. But in principle, there is nothing else that can stop a different kind of life, right?
That's
You
right.
just have to have a certain properties of life. Life has to metabolize, life has to reproduce, life has to do certain things, and you can have another kind of life which is not carbon-based. It could be silicon-based. It could be life. It doesn't depend upon water, right? We know that on the earth itself, we have life forms which don't need water, which don't need oxygen. And therefore, when it comes to space, you could have any kind of life, right? So, in principle, nothing is ruled out. I mean, if you
Yeah.
actually see science fiction books, there are even kind of life forms which you can have on Jupiter also,
That's
right?
right.
So, in principle,
So
anything is
thank you
possible.
so much. Yeah, thank you. And we have Tushar who would like to ask his question in voice and in Hindi. So Tushar, you can unmute yourself and
Yeah.
ask the question.
I'm audible.
Yeah,
Yeah,
you're
yeah, you are.
audible very much. Yeah.
थैंक यू फॉर थैंक यू फॉर मुझे परमिशन देने के लिए। मेरे मैम से 2-3
Welcome.
सवाल है, लेकिन पहला सवाल है कि आपने एक स्लाइड में बताया था कि एक एप्लीकेशन या वेबसाइट के बारे में, क्या उसकी लिंक वगैरह ऐसा कुछ संभव है कि वो शेयर कर सके ताकि उससे ज़्यादा जानकारी मिल सके? अगर जिसको यहाँ पे पता ना हो तो उसके लिए बोल रहा था।
नहीं, जरा आप रिपीट कीजिए, क्या पूछ रहे थे आप?
आपने एक पीपीटी स्लाइड के अंदर वेबसाइट या एप्लीकेशन के बारे में बताया था। वो क्या था? वो उसके बारे में थोड़ी जानकारी दे सकते हैं क्या कि
कौन
जिसको
से
जिसके
एप्लीकेशन, ये कॉन्टेस्ट के लिए?
नहीं, अभी आप अभी पीपीटी स्लाइड दिखा रहे थे ना, उसके अंदर
जी।
एक नीचे लिखा हुआ था, इसलिए बोल रहा था। डाउनलोड
किस चीज
करने
का एप्लीकेशन? मैं समझी नहीं, किस चीज का एप्लीकेशन?
ये सब कुछ अभी आप जो बता रहे थे उस समय एक स्लाइड के अंदर
मैं
लिखा
ठीक
हुआ।
से समझी नहीं, किस चीज की एप्लीकेशन आपको? पीपीटी चाहिए क्या?
नहीं, पीपीटी नहीं, पीपीटी के अंदर लिखा था कि आप इस एप्लीकेशन या वेबसाइट पे जाके ज़्यादा जानकारी के लिए एक कर सकते, इस तरह से लिखा हुआ
अच्छा,
था।
नहीं, हाँ, तो
वो
मैंने
वो
ये लिखा था कि चूंकि ये फील्ड में बहुत ज़्यादा चेंजेस आ रहे हैं, तो आप इंटरनेट पे नासा के वेबसाइट पे एक एक्स्ट्रा सोलर एनसाइक्लोपीडिया, ऐसे कई वेबसाइट्स है जिस पे आप नया इन्फॉर्मेशन आप देख सकेंगे एक्सोप्लैनेट्स के बारे में। तो वो था मेरा कहना कि चूंकि ये फील्ड में इतने चेंजेस आ रहे हैं, तो आप ज़रूर वेबसाइट्स को देखिए, इंटरनेट पे देखिए, क्योंकि यही एरिया में बहुत नए चीज़ें हो रहे हैं, तो वही एप्लीकेशन है वो।
ओह! मुझे लगा कि खास तौर पर कुछ जैसे एस्ट्रोनॉमी के लिए मोबाइल एप्लीकेशन होते हैं, जैसे कि स्काई सफारी, इस तरह से कुछ होगा
अच्छा,
बोल के।
वैसा एप्स, ओके, नहीं, कुछ, अच्छा, ठीक है, अब मैं समझ गई। तो कुछ एप्लीकेशंस है जिससे आप सिटीजन साइंस प्रोजेक्ट्स कर सकते हैं। तो सिटीजन साइंस प्रोजेक्ट्स में कुछ प्रोजेक्ट्स है जिसमें आप प्लानिटरी हंटर्स ऐसे कुछ है, तो उनके एप्स है, उनके एप्स आपको इंटरनेट पे मिल सकते हैं। एक्सोप्लैनेट हंटर्स या प्लैनेट हंटर्स एक बोल के है। अभी मैं ज़रा उसका देखती हूँ, अगर ओके, तो ये तो एक एप्लीकेशन है। फॉर एग्जांपल, अगर आप गूगल प्ले पे जाएंगे तो एक प्लैनेट हंटर बोल के है, राइट? तो ये एक है, और एक और है प्लैनेट हंटर्स, आप प्लैनेट हंटर को ज़रा देखिए गूगल प्ले पे, और उस पे आप देख सकते हैं, ठीक है?
ओके,
तो
ओके।
वैसे कुछ है।
थैंक यू।
Thank
वो
you so
मोबाइल के
much.
अंदर चलेगा ना? क्योंकि मेरे काफ़ी दोस्त हैं जो इस तरह के कॉन्टेस्ट में भाग लेना चाहते हैं, लेकिन प्रॉब्लम ये है कि उनके पास पीसी या डेस्कटॉप नहीं है, सिर्फ मोबाइल फ़ोन है। क्या वो
नहीं,
मोबाइल
तो
से भी
कुछ
कर
खास है जो मोबाइल फोन्स पे होते हैं सिटीजन साइंस के। तो एक्चुअली मैंने कई टॉक्स किए हैं सिटीजन साइंस प्रोजेक्ट्स जो आप यूज़ कर सकते हैं आपके फ़ोन पे। तो वैसे कई
ओके।
है, जरा आप गूगल करके सिटीजन साइंस प्रोजेक्ट्स भी देख सकते हैं, उस पे भी आपको इन्फॉर्मेशन मिल जाएगा।
थैंक यू। दूसरा मेरा ये सवाल था कि अभी आपने बताया था कि अगला सेक्शन हो गया या फिर अगली टॉक होगी, आपकी मीटिंग होगी, उसके ऊपर आप थोड़ा और ज़्यादा विस्तार से बताएँगे। वो कब होगा? और इस तरह की और जानकारी आप कहाँ से मिल सकते हैं? उसके लिए वेबसाइट है, ऐसा कुछ ग्रुप वगैरह है क्या? तो जहाँ से जो भी इसमें दिलचस्पी रखता है वो जॉइन होके आगे की जानकारी प्राप्त करता रहे, अगर
जी,
पॉसिबल हो तो?
जी। तो ये आप आपके वजह से मैं अब अपना ही क्या कहते हैं, अपना ही एडवर्टाइजमेंट कर लेती हूँ, आपको बता देती हूँ। ये एक्चुअली मैं काफ़ी आउटरीच एक्सेट्रा की कोशिश करती हूँ। तो आपको बता दूँगी, ये देखिए, ये मेरा वेबसाइट है, ये है सृष्टि एस्ट्रोनॉमी, ओके? और ये सृष्टि एस्ट्रोनॉमी वेबसाइट पे जैसे अभी वेरी सून एक वर्कशॉप होने वाला है 8-9 अक्टूबर को, जब हम लोग कुछ और रोबोटिक टेलीस्कोप्स के बारे में बात करेंगे, राइट? सिमिलरली अगर आप ये वेबसाइट पे जाएंगे तो आपको इसमें भी कई जानकारी मिल जाएंगे चीज़ों के बारे में। इसमें अगर आप प्रोजेक्ट्स में जाके देखेंगे तो आपको कई चीज़ें मिल सकते हैं यहाँ पे इंफॉर्मेशन। ऑब्वियसली कई और भी जगह हैं जहाँ पे आपको इन्फॉर्मेशन मिल सकता है, लेकिन अभी फ़िलहाल के लिए आप ज़रूर वेबसाइट को जाके इसको रजिस्टर कर सकते हैं। ये वर्कशॉप होने वाले है अगले वाले वीकेंड को, ये वाले नहीं, यानी कल परसों नहीं, लेकिन इसके बाद वाले वीकेंड को ये एक ऑनलाइन वर्कशॉप होगा स्टेलर फोटोमेट्री पे। तो ऐसे कई होते हैं, और ये ऑब्वियसली सभी फ्री होते हैं, इसमें कुछ चार्जेस वार्जेस कुछ भी नहीं रहता है। ठीक है, तो आप इसको रजिस्टर कर सकते हैं।
थैंक यू।
ठीक है।
और मेरा और
Yes.
2 सवाल है।
Mr.
एक और
Mr.
सवाल है।
Tushar, can you
हाँ।
mail to us and we will forward to
जी,
ma'am because there are few more
हाँ,
questions.
मैं वही
Yeah,
बोलने वाला
yeah.
था कि आपकी
Thank.
ऑर्गेनाइजेशन का वेबसाइट वगैरह कुछ होगा तो वो देखेंगे तो अच्छा रहेगा,
Yeah,
जितने
yeah.
भी क्वेश्चन है
Surely we
वो।
will share and
एक
ma'am.
लास्ट क्वेश्चन है, प्लीज़, एक लास्ट क्वेश्चन है, वो ज़रूरी है। मैंने जैसे ड्रॉप आउट या जो 9th ड्रॉप आउट है या फिर 10th पास है और जो इस फील्ड में आगे बढ़ना चाहते हैं, लेकिन उनके लिए क्या बोलते हैं 12th का नॉलेज नहीं है, तो वो आगे बढ़ कैसे सकते हैं और करियर किस तरह से बना सकते हैं? वो ये सवाल मेरे ख्याल से ज़रूरी है सभी के लिए, जो ड्रॉप आउट स्टूडेंट है उनके लिए तो खास तौर पे होगा मेरे ख्याल से। इसलिए पूछ
Sure.
रहा हूँ।
तो
थोड़ी
एक्चुअली
ज़्यादा बोला हो तो।
ये फील्ड में आने के लिए आपको बेसिकली मैथ्स और फिजिक्स करना पड़ेगा, मैथ्स और फिजिक्स पढ़ना पड़ेगा। तो आपको बीएससी, एमएससी, मैथ्स एंड फिजिक्स, फिजिक्स स्पेशलाइजेशन, मैथ्स भी चलेगा लेकिन प्रेफरेबली फिजिक्स करना पड़ेगा, राइट? तो अगर आप दिल्ली के हैं, आप कहाँ के हैं?
मैं मुंबई से हूँ।
अच्छा, तो मुंबई में भी बहुत सारी फॉर एग्जांपल टीआईएफआर बॉम्बे है जहाँ पे एस्ट्रोनॉमी का ग्रुप है। जेवियर्स कॉलेज में अगर आप बॉम्बे में हैं तो जेवियर्स कॉलेज ने कुछ साल पहले ही स्टार्ट किया है एमएससी प्रोग्राम फिजिक्स में, जिसमें स्पेशलाइजेशन है एस्ट्रोफिजिक्स का। ठीक है, तो आप ज़रूर वहाँ जाके एमएससी कर सकते हैं, या आप वहाँ जेवियर्स कॉलेज में जाके लोगों से मिल सकते हैं, क्योंकि उनके पास कुछ स्टाफ है जो एस्ट्रोनॉमी के है, तो तो वो लोग आपको गाइड कर सकेंगे। तो आप बीएससी करके वहाँ एमएससी कर सकते हैं या दूसरी जगह पे भी कर सकते हैं, और बाद में आप पीएचडी भी कर सकते हैं। तो जेवियर्स में ज़रूर जाके मिलिए आप स्टाफ से वहाँ पे बहुत अच्छा फिजिक्स डिपार्टमेंट है, और वहाँ पे एस्ट्रोफिजिक्स है, तो आप वहाँ जा सकते हैं। ठीक है।
Thank you so much, Dr. Priya and Mr. Tushar. We move on to the next question by Dr. Mashmi Das. The extraterrestrial life existence can also be possible to detect. She wants to ask whether we can detect this.
See, life like I said, spectroscopy will give us chemistry, right?
Yeah,
So
yeah.
in that way we can, but just getting, for example, amino acids needn't imply life, right? Then there is contact and all that. So it's not very easy to answer this, because existence of life is a different thing. ये अभी तो हम लोग बस देख रहे हैं possibility. So we are at present still stuck on possibility. But detection means, number one, chemistry, number two, some kind of contact. So it can obviously be possible to detect it, to do it, but obviously abhi to it's a bit too early for us to reach that stage of detecting. At present, we are at the stage where we're just looking for exoplanets, for habitability, for chemistry. But to actually confirm life is a difficult thing, but it will happen. It will happen with time.
Because on Earth also it has evolved over billions of years and it has taken so many forms, and detection truly will be a challenging thing, and it may be possible with advent of other techniques and other advanced techniques in near future, and that may not be possible, or possible, I think, is difficult to say.
Even
Next is
human
by,
beings. Yeah, we have
yeah,
also not always been contactable, right?
yeah,
We are
yeah.
communicable. Radio is just the last 50, 60 years. Otherwise, we can't contact. We couldn't have contacted any life forms, right?
That's right.
So, yeah,
Next
so you're
question is by Mr. Lakhani. Can you tell anything about planet's revolution and rotation? As it is very important, like, can we say that the planet is tidally locked or not?
Yeah. So what I will show you all in the demo, we will actually see how we can get the revolution period of the planet. We can get the revolution period. That's quite simple. But detecting the rotation is more difficult. So we actually, if you want to do rotation, you'll actually have to do it with some kind of spectroscopy. So at present, according to me, we don't have a means of getting extrasolar planet, getting their rotation. Revolution is easy, but rotation is a little difficult. So,
Okay, thank
but
you.
but people are actually doing it. Like I said, you'll have to do it with spectroscopy. So I'm just now Googling and seeing. So there is a young extrasolar planet for which people actually did spectroscopy and got some kind of this thing. So they can. So in principle, it can be done. You can do it through spectroscopy. So through spectroscopy, you'll have to use the Doppler shift. And with the Doppler shift, you can actually get it. So yes, you can do that. And with that, they can find out whether the planet is tidally locked or not. Yes, it can be done. In principle. In principle.
So again, data analysis can help more in this.
Yes. Yes.
So next question is by Kritika. She's asking, thank you for the wonderful session, ma'am. I have a general doubt. I guess based upon planet's environment, the elements present in it, life is forming. If it is true, how can we say life on the exoplanet is based on water and temperature? And if it is, what is the possible methods to find life on exoplanet?
Yeah, so thanks, Kritika, for that question. So, like I told you, when we are talking about life as we know it, we are looking for water and temperature, because we think that those are the two essential things for life. But in principle, you could have life forms which live on higher temperatures or lower temperatures, as well as do not require water, right? So, so if we actually, based on that planet environment, we can estimate whether what is the temperature and things of that. But so this is the way we are starting off, right? But obviously, so that's the way we are doing it, looking for habitability as well as looking for chemistry. So that's a possible method to find life for chemistry. And then other ways through contact, right? So you actually have the SETI program where they actually look for radio signals from aliens to actually look for, whether are there any radio signals which seem to be coming from this thing. So The SETI program is a fixed program which actually looks, it's a search for extraterrestrial life. So there are many ways in which people are trying to look for it, but it's obviously not an easy thing, right? It's not an easy thing because, you know, communication also with we barely communicate with animals on the planet, right? So if you want to actually communicate with aliens, that's a different story, right? We do not know very well how to do that.
Yes, indeed. And thank you so much. I will invite Dr. Chawla to ask her question. Dr. Professor Chawla.
Hello.
Yeah.
Yeah. Hello, Dr. Hassan. It was very wonderful. I'm from microbiology background and it was nice. And I mean, it's a totally different story to hear about these exoplanets. So I learned something very new today. And
Thank you.
you just, you gave the talk in such a simple manner that it was very, very well understandable. So my question was, first question is that can we find age of these planets? I mean, are there methods available to find the age? Because then
Yeah.
probably we can correlate with the age of the Earth.
Okay, so finding out the age of the star is
Yeah.
quite easy. That is not difficult. We can find out the age of the star. And if you assume that the planet formed with the star, which I showed you, right, that generally with our understanding of star plummet formation, they form together. So in that way, you can find out the age of the planet because you can find out the age of the star, right? But for example, on the Earth, when you want to do dating of rocks, we do it using radioactivity, right? So what they do is you take rock samples, look for the radioactive decay. So for example, you look for the abundance of carbon 12 versus carbon 13, right? Or any radioactive materials. And using that, you can get accurate dating, right? But for that, you need to get a sample, which we don't have. We don't
Which
have
we
the
can.
pleasure of getting the sample. So
Yeah.
the only way I can think of it is you can do it by finding the age of the star. The star we can find out. That is quite doable. With that, we can find that out. Yes.
Thank you. And one more thing, like the last question you were answering. So there have been reports that NASA is probably in contact with aliens. So what is your say on this?
I don't know. There's so many of these conspiracy theories of all
Yeah.
kinds of things, and I don't think that's true. But
Yeah,
but
it's
obviously there
difficult.
are various
Yeah,
theories
the
of that.
fact you have told is actually true that we do not understand their language or expression or anything about them. So
No, no.
we
So I would say that if there is, then one has to follow the scientific method where you look for scientific evidence, right? So, for example, if you say NASA found an alien who's hiding over there and kept over there, then we need some kind of evidence of that thing, right? And based on the evidence, yes, you can say yes, NASA has it or doesn't have it or did whatever, right? But we need evidence. We can't just go on because somebody said that they do have something, there's some big secret they're hiding from us which we don't know about. That will obviously, that's not convincing. So if we want to be convinced, there has to be some valid evidence, right? So when they or whoever it is puts forward that evidence, that this is the evidence, you are in contact with an alien and you give some proof of that, then one
definitely.
can question the proof and believe it. But till the time you don't have any evidence of it, you can't
Hmm.
believe it. But like
Correct.
I said, the important thing that the possibility that life is there in the universe is very, very
Yeah,
high.
yeah, yeah.
So
Being a microbiologist, I understand mostly we find microorganisms, to
yeah, so
begin
there
with.
are amino acids all over the universe. There are lots of organic material is there. And therefore,
Right.
the possibility of life is high. There is a very high chance that there is life. But obviously, contacting it and all that is the problem. But,
Hmm.
but for us to believe it, we need evidence. Let us get
Right.
evidence, then then we can believe it. Till
Thank
then,
you. Thank you so much. Yeah. Thank you for the answer.
Yeah,
welcome.
thanks. I have a very small question, Dr. Priya. I just want to ask that the Titus Board law is applicable to the planets of our solar system, in which the distance of the planet from the sun and their and the spacing between them is
Yeah.
actually follows the empirical law. What about this law applicability to other exoplanets? Has it been tested or has it been tried?
Yeah, so actually, this both law, what happened is that it fits in very well for our solar system, right? But the problem
Except
is
the
that
last two. Except the last two planets.
Yeah, it does not fit in for all, only for the without the last two. Correct.
Yeah.
But the problem is that it does not have any physical basis, right? So if you were to actually use Newton's law of gravitation, which will define where do you have the orbits, right? This law does not have any basis of that kind, right? What is more true, what happens, since you are from physics, you know, there is what is called resonance, right? So there, in every orbit, you have a certain frequency, which is defined by the orbit. And between these orbits, there are frequencies. So for example, Saturn's rings, Saturn's satellites, Jupiter's satellites, even the planets of our solar system, they have certain, you know, frequencies where there is resonance, right? And those resonant frequencies are there. But in principle, there no physical basis of this thing, and therefore it's basically Tish's law, board law is not exactly accepted by the scientific community. It's just a rough law which predicts the spacing, right? It somehow predicts it, but in principle there is no there is no physical basis for it. So what happens is, it's okay for Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus. Neptune, Pluto don't go. So we, in principle, since there is no physical basis for it, we haven't this thing. But yes, it's an interesting thing, and it could probably be checked for.
Because that will provide an interesting problem to the students, because the absence of the fifth planet and the presence of asteroid belt at that place, according to Bohr's law, as well as this is empirical law, but that law is actually giving a good estimate of position of planet from the sun. So if it is tried for other planets, exoplanets also, I think that will be, in spite of not having any physical, say, origin, but this is empirically giving a good, say, estimate of the distances. So that is something interesting to be tried for other planets, exoplanets also.
So actually, while you asked me, I just now checked. So actually, there is a paper of somebody who tried to verify Tish's law for exoplanets, and they actually tried doing it, and they used Kepler data itself for multi-planet systems, and actually tried to look for this thing. So what they found in their result is that it did not satisfy. That's what I can see in this paper. They did it for 56 exoplanet systems, and for the 56 exoplanet systems, it's a paper of 2014, and they said that they did not find it. But
so at that time, the number of exoplanets detected were very less. Now the number is more, so it can be tested.
Yeah, it can. Yeah, you can still give it to students to check and see.
That's right. That's right.
So
there is another comment by Kritika. She's saying, is there any possible communications other than radio frequency? And that will be our last question for this session, because already we are running late. But I think all the questions were so interesting that it is very difficult to stop in between, because that interaction is also a part of this kind of meeting. So that is what I feel that we have, that is why we have taken these questions. But sorry for the delay, because of which it has caused a delay. So this question is by her, and she's asking, is there any possible communication other than radio frequency?
Yeah. So in principle, obviously, communication at the frequencies can take place. The thing is that for the Earth, for our atmosphere, if you see, radio frequencies are the ones which pass most easily from our atmosphere, right? And therefore, if we want to actually have communication on the Earth, for that, radio frequencies are the ideal frequency, right? And what happens is, with longer wavelengths, what happens if you're in shorter wavelengths, energy gets absorbed very easily. But at longer wavelengths, it can move much faster and better. And therefore, generally, what is considered that longer wavelengths, which are radio wavelengths, are longer wavelengths, they are considered better for communication because they can pass through much more easily, right? But in principle, and for the Earth, because the other frequencies will not come down to to the Earth, right? And even when we want to do communication with any satellite also, again, we need to do it with an Earth-based system. And therefore, we all the time look for radio frequencies if we are looking for the Earth. But in principle, you can have communication on other ones. But like I said, if you are at higher frequencies, then the amount of absorption, etc., is going to be much larger. So in principle, this is the preferable one. This is the preferable one. to actually have it at longer wavelengths and low frequencies. They are the preferred frequencies for communication.
Thank you so much. And what do you suggest? Can we have a break of 5 minutes before we start the next session?
Yeah, we can surely.
So
Yeah.
really apologize for being a little bit late, and I think you will compensate for that in the next session. You can
Yeah.
take your call, because you can decide on your own how much depth has to be done and how much time will you take. Thank you so much.
Should I exit this thing now? Or?
No. We can be muted, and we can stop our video, and then we can join back after 5 minutes.
Yeah.
In the
Okay,
same meeting.
Yeah. Okay. Yeah. I'll just call you.
So, good evening. We begin the second session of demo with Dr. Priya now. Hello, Dr. Priya, are you available?
I don't see her, Vandana.
I think she is here. She will just join in a minute or so.
Okay.
Yeah, I'm here. I'm here.
Yeah.
Okay. Shall we? So let's start, right? Because we
Yeah,
are
yeah.
running
Yeah.
late. So
Yeah,
you said you want me to do some of that this thing, some of the Kepler
Yeah.
part.
Yeah. Using the software, accessing the data, and what kind of analysis students can do in order they want more on this. So that will be wonderful because this will be starting point for some of them.
Okay, fine. I'll just 1 second.
But I'm sure we need to keep another session for you.
Yeah. Do this. Okay. Fine. So I hope you can see my thing. You can see my
Yeah,
screen.
it is visible. Yeah, it is.
Okay, so this is
visible.
actually another. I just move from here. This is. Oh yeah. So I would first of all I would like to thank my friend Tim Hamilton. So Tim Hamilton is an astronomer, a friend of mine whom I made over the internet, and we actually did some work together. And the demo which I'm going to be showing you is based on the demo he had done for us for our students. And then I mean I learned it from him. And that's what I'll be doing it. So I'd like to thank Tim Hamilton for his thing.
Thank you.
So we are going to see in this demo how can one use Kepler data to actually get to study exoplanets. Now, like I mentioned to you, Kepler data is basically transit data. So you have a planet coming in front of the star and you have a fall in the brightness, right? So that's what you're going to see in this. So we saw this earlier that it's a ratio of the radii. And this is the other one, that how do we do it? Now, what are we going to do is we'll use Kepler data to actually find the orbital distance, the radius of the planet, the mass of the planet, the temperature of the planet, as well as, and then not exactly the chemical composition, but the density of the planet. So that would kind of give us this thing. So what I'm going to do is I'll stop sharing. And now I'm going to show you how do you access the data. Okay. So to access this data, you can see my Chrome screen, I think over here, right? You can see my Chrome, right? So to access the data, I'll just close these things. I'm sorry, I have multiple tabs. Okay. So there's a website called Must, which is you'll see, what you all you need to do is just Google for Must, right? This is the Barbara Mikulski archive for space telescopes. Okay, this has data for various space telescopes. So you can just, if you don't worry about the website, just do Must Astronomy. You'll see Must Home. This is the website. Click on this, you'll come onto this, right? And this website basically has data of even JWST data is available on this. This has Hubble. This is the JWST data, the test data, and various missions which have their data over here. So you can click on this thing, see all of Must missions and data. And if you click on this, you will obviously see a whole bunch of it. And we are going to look for Kepler. So we want Kepler data. We do legacy mission, Kepler data, right? Now over here, you can see the description of Kepler data, which is over here. Basically, it observed a certain part of the sky and it continuously observed that. And using that, it basically, so what you're going to do is go on to menu, right? And you need to look for the HLSP, high level legacy programs, right? And in this, if you actually go on, You scroll down. I'm sorry, I'm going a little fast, but we don't have much of a choice because I need to hurry. So you're going to look for this and you're going to come out to Kepler. Okay. So you can look for when you come onto this, you can look for Kepler. And I think I've already opened over here. So this is the Kepler website. I will share this. So I can share this website with ma'am and she will pass it on to the other students. Otherwise you can, okay, even in WebEx, I can probably this thing it. I'll just look for it in WebEx chat. Okay. I don't know where is the WebEx chat. Okay, anyway, ma'am will share. So this is the thing. Okay. Now over here, there are two data sets. This one, the _DTR is the one which we have with Kepler data. And this RVB, what happened is what were the sources which were observed with Kepler? Ground-based telescopes use their spectrographs to actually get radial velocity data because Kepler does not have a spectrograph on it, right? And therefore, what was done is Kepler would just get the light curves, and then the ground-based telescopes, they would actually get the radial velocity. So both the data is over here. And if you look over here, there are example of a few Kepler sources which are there over here. So typically, let us go for the first one. Please click on this. If you click on this, you need to download both these things. This is the time series data, and this one is the radial velocity data. So if you click on it, right, you can directly download this data. So this, if you can, so you'll save it over here. And what you can see is that this is a source which is called Kepler 6b. Like I told you, Kepler 6a will be the star. Then the planets get counted from B, C, D, etc. So here you can see there's a set of Kepler sources which are shown over here. I'm taking Kepler 6b, you'll take this one, right? And then like ma'am has mentioned to you, we are using a software called TopCat, okay? So if you Google over here, you can actually say, again, you say TopCat and you'll get this. This is TopCat, or do TopCat astronomy, right? So that it does not go into this. So you will do TopCat over here. And I'm going to go a little fast so that later on you can see the recording and you can finally do this. So if you go on to TopCat and you'll come on to downloads, you can download it from here. TopCat is a Java-based file, so it doesn't make a difference to it what is your operating system, whether you're using Windows, Linux, Mac, whatever. You can download this TopCat full.jar. And you need to have Java running on your system. And then when you double-click the file, you can actually run it. I already have TopCat with me, and therefore I can open it. So I am going to open it from my own TopCat, but in principle, you will use your TopCat, right? So TopCat download is very, very simple. There's no problem at all in installing it because it is Java based, right? So your operating system, like I told you, doesn't make a difference. I hope you can see my screen. Let me just check whether, can you see?
Yes.
You can see the TopCat
Yes,
window?
it is visible. Yeah, it is visible.
Okay. So now what I'm going to do with TopCat is I'm going to load that data which I showed you. Okay. So it is sitting in a certain location on my system. So I will just go there. Right. So there are the two files. This one is the light curve and this one is the radial velocity one. So click on the light curve one, right? This is the table format. This is plain ASCII format. So you're going to go into ASCII, do ASCII, say OK. And this is the file. Okay. Now TopCat lets you plot data. So you have to click on this window, right? And okay, so if you look at the table, this table is just made up of column 1 and column 2. So column 1 is the time, the dates. Column 2 is the brightness, but the brightness has been scaled. Okay, it's been scaled to 1.
This is not visible. Columns are not visible now.
Okay. 1 minute. I'll just, okay, because it thinks it's sharing Chrome. I will just share, I want to share the whole screen. Okay, then this should be fine. I think now you can see it. Yeah, I think now you can see.
Yes.
So you can see that this file, if you see, it's made up of 2 columns. This one is the dates. This is in astronomy, we have something called Julian dates. And these are the Julian dates, right, of these things. And this one is the column 2, which is the brightness. You can see the brightness is 1.99, something like that, right? Because the fall in brightness is just like 0.99 types, not much. But these are the dates. So if I plot it, if I were to plot column 1 versus column 2, you'll see this. This is your plot, right? So what is the plot? Is that you can see this is the brightness of the star, which is around 1, and it's getting fainter, dimmed by barely 0.01, right? You can see this is 0.99. Remember, I was telling you that the fall in brightness is very, very small, very small, very difficult to detect, and therefore you need a space-based telescope to detect that. So you can see the fall is like this, right? It is very, very small. And so in the star is like this, then it became faint, then it became faint. So every time the planet came in front of it, it became faint with a certain period. Here you have a bigger gap because what happens with Kepler is it looks at other places and then comes back to the same thing. So probably here there was a gap when you see there's a clear gap in the observations. Here also it's not there, here also it's not there, and you don't have these observations, right? And therefore, now what we want to do is this is called the light curve, but we want to study the light curve in more detail. And therefore for that, we do something which is, you can see the screen of mine, this is the plot you're seeing. I hope you can see this. You can see my presentation, right, ma'am? Ma'am, you
Yeah.
can see my presentation?
Yeah, it is visible.
So
Right
can
now,
you-
you are showing the graph. It is column 1, column 2. Yeah.
No, can you see folding functions?
Yeah. Now it has appeared.
You can see folding functions. Okay.
Yeah.
So what we see is that the light curve is something like this, right? You are seeing a fall and a break and this and that, right? And therefore what we do is I want to see the light curve in more detail. And therefore what I do is I fold it. So just think of this like a long strip of paper, right? I have a long strip of paper in which I am getting some variations, right? I will just try to get something. So I have this long strip of paper. Now what I do is there are peaks coming, right? These peaks. And therefore I fold the paper so that all the peaks come one on each other, right? This is a standard procedure which is done even in signal processing, right? If you have signal processing, I am not sampling the data at every point. At every point, I don't have a point, data point, right? But here I had it over here I have it at some other point, at some different points. And therefore what I do is I fold the data so that I can get this whole data, right? Now, how do I fold it? In this case, when I fold it, I use a function which is called the modular function. Modular function means what? For example, if I have 12 and I divide it by 3, the quotient is 4 and the remainder is 0. So the result of the mod is 0. But supposing if I take 12 and I divide it by 5, the quotient is 2 but the remainder is also 2 and therefore my result is 2. If 15 by minus 3, it will be minus 5, remainder is 0, right? 10 divided by 3, I do it, so I will get 3 5s, I will get it like that, right? So what I get it like this, and therefore we use this function which we call the modular function. Okay, so I'm going to fold this light curve and I will get the modular function. So I'm going back to TopCat and I'm seeing this over here. And while I have these columns over here, I am going to cheat a little bit because I know the folding has to be done in terms of the time period, right? The folding has to be done in terms of the time period, okay? And therefore, what I do over here is I create you have to go to this upper part, right click over here, say new synthetic column, right? And I'll say mod, and now I'll say modular function. So my modular function is made up of column 1 and the comma, the folding is going to happen, or I'm going to divide by the factor, which is the time period, right? So if I do the wrong time period, supposing I do 3.5, right? You'll see it over here. And when I plot it over here, you will see it's coming like this. It's not giving me a good idea. So if I take the exact, you have to do this on a trial basis, trial error basis. But since we don't have time and I'm this thing, I will use modular call and I will put the time period. The time period for this particular exoplanet is 3.2346 days. Okay, so I'm going to put this and I will say this is this. Okay, so say call 1. Okay. And here what I'm going to do is I'm going to make it in terms of mod. So now you can see what have I done is I've got all these changes. Remember that earlier function which I had, I'll show you. This was the earlier plot I had. Now what I've done is with this period, I've folded it. So once I've folded it, I have got this plot, right? And now in TopCat, I can just use axis so that I can change the range. And if you see, this is somewhere around 3, right? So I'll take it as 2.9 divided by 3.2, right? So you can see this. Now you see, now I'm getting a light curve. But this light curve is made up of points which were derived at all different times. But because I divided it by the time period, the modulo, I got this value, right? Compared to what I had got if I had got the first plot. Once I get this, now I know my time period, right? Because you are first going to play around with this, with the modular function, so that you get the time period, right? And if you got the correct time period, you will get a nice curve like this. If you did not get the correct time period, you will not get a curve like this, okay? So you will use this to actually get your time period. Now what I'm going to show you is that once you get your time period, right? You can see my slide. We have our time period, right? And here, if you move ahead, we have our time period. Now the next thing is we want to do is we want to measure the distance of the star to the planet, right? But because we have our time period, you'll all remember Kepler's third law. What is Kepler's third law? P squared is proportional to A cubed, right? That means the square of the time period is giving you the cube of the orbital radius. So if I want the orbital radius, therefore A cubed by P, this thing is this, right? I'm sure all of you all know this formula, right? You all know this formula, which is Kepler's third law. And if I assume that mass of the planet is much, much lesser than mass of the star, so I can forget about this MP. So I just have that A cubed by P squared is equal to this. A cubed is equal to this, right? So what do I have to get my orbital period? Orbital radius. I already know my period. My period is 3.2346 days, right? Now I know this. So I can find out this. Only thing is I need to find out mass of the star. Okay. How do I find out mass of the star? So you need to go to this website called exoplanet.eu. Okay. Go to this website and there you will find out, you will have to find out the value for Kepler 6b. What is the mass of the star for Kepler 6b? In principle, I think if you even Google, just say mass of star for Kepler 6b. Sorry, 6b. So you can see it's over here. Its mass is, this is the mass of the planet. So mass of this thing for, you can, yeah, it's available on that website. So you can get 6b is obviously the planet, but we need to get the star. This is the mass of the star. This is the host star. So the host star is given over here, and you can look over here and you will see its mass. So it's 29.29 times more massive than the sun. So with that, you can find out the value of the mass. So actually the mass of it is about 1.21 times the mass of the sun, right? So if I substitute in this formula, which we already saw over here, in this formula, if I substitute this is 1.21 times mass of the sun, I then have to convert that into kgs. So you have to multiply 2 into 10 power 30. Similarly, your period, which is 3.2346 days, convert it into seconds because that will be SI units. Once you do that, substitute it in this formula, you will get the value of the mass of the, you will get the value of A, right? So first thing you can find out the value of the orbital radius, which is A. The second thing is what we want to do is to find out the size of the planet. If you remember when we were doing the size of the planet, I told you that the radius of the planet is going to be this, right? Radius of the star multiplied by the ratio. If you remember, this F trans is 0.99, right? Remember what we had in the plot. Look at the plot. You had 0.99. If you come somewhere over here, you'll see 0.9894, the number which is down here. Look at this area. You'll see the number which is down here, which is also 0.9895. So this is your F trans. This is the value which you're getting for this, right? Similarly, in our earlier Google search, which we did, where we saw the mass of the star, we also saw it's 39% larger than the sun. So the radius of this star is 1.39 times radius of the sun. And therefore, ma'am, I hope you can see everything, no? Yeah.
It is all visible. Yeah.
Very good. So you are going to take 1.39 times the size of this thing and substitute in this. So here we'll take radius of this star is 1.39 times radius of the sun. And you'll take 1 minus, this is 0.9894 divided by 1, right? So with that, you can find out the size of the planet. Okay. The next step is you want to find out the temperature of the planet, right? So how are we going to find out the temperature of the planet? We are going to use Stephen Boltzmann's law. You will say luminosity is equal to 4 sigma Tp for Rp. We already know Rp, which is the radius of this thing. If we take the ratio of the luminosity of the star as well as the planet, you can get this formula, which is temperature of the planet is T star into this. So T star was also there on Google. If you remember, when we checked it over here, the temperature was given of the star 5647 Kelvin, right? 5647 Kelvin. And therefore, you're going to use that itself so that you can substitute over here 5647. And here you'll take radius of the star and orbital distance. We have already found it out, right? Alpha is called the albedo, or it is how well does the star reflect light, okay? And in the case of planets, generally we take the alpha value to be 0.07, something like that, okay? So we can take that value, substitute that, and find out the temperature of the planet. The final thing is the mass. The mass, for that we have to use the radial velocity curve. So we are going to get this value from the radial velocity curve, the maximum velocity. This we already know. This is the orbital radius. This is the mass of the star we also know. G we know, 6.67 into 10 power minus 11. I, inclination we do not know, so we will assume sine I is equal to 1. So therefore, what you have to do now for the radial velocity curve, again open TopCat, open the in TopCat, load the table which has the radial velocity data, right? We plot the radial velocity data. You can see it over here. This is the radial velocity. This is the time. Take the maximum value of radial velocity, either minus or plus, any of them. You can see this one is the lowest value, which you can read down. See over here, you can read it. It's coming to be 75. Okay. So if you put 75 into this formula, you will see that your 75 into this all will give you this, and you can get the mass of the planet. Once we know the mass of the planet, we'll find out the density. The density is mass upon 4 by 3 pi r cubed. That's the density. And here, if you look at this plot, you will see that depending upon the density, it will give you the chemical composition. So once you know the density of your source, look at these things over here. If you have an iron planet like Venus and Earth, the value will come somewhere over here. But if you have Uranus, Jupiter, Uranus, Neptune types, they'll be over here. Jupiter, Saturn types, they'll be over here. And you'll see that our object is going to come somewhere on top over here. It will come somewhere over here. So actually, unfortunately, because of the lack of time, we could not do all these things. But I hope that you all can see the video and try doing it. I will share this thing with you. But with this, you all will discover that this object which we get is actually a hot Jupiter. It is an object which has a mass close to Jupiter, but it is very close to its star, and therefore it's a hot Jupiter. So I had placed an assignment over here for students, level 2 levels. One is you can do this analysis with Kepler data for these sources. We've already done it for 6B. You can do it for these sources. And the level 2, one is to repeat what I did today. And the level 2 is to do the analysis with Jupyter Notebook, right? So that is this brief thing, but I'm sorry I had to run through it, but we didn't have a choice. Okay. So please try doing this and let me know if you have problems. I will share with ma'am another video of mine which has very details of the same analysis which I showed you today. So that is a very long video. It's almost 2 hours. And you can try seeing that and using that to actually do this analysis. Okay. So I will share that video with you all and probably that will make it easy. Okay. We'll now move on to the final part of my thing, which is NameExoWorlds. Okay, so most of you all have heard about James Webb Space Telescope, right? So this is an infrared telescope, 6.5-meter telescope, which is out in space. It was launched last Christmas, right? And now it's already taking data. Some of you all may have seen its first images. So for example, this is one of the early images of James Webb, which is of a star-forming region called Carina Nebula. So this Carina Nebula is a star-forming region where very young stars are being formed. Okay. Other than that, so it's measured it and it's doing this. Other than that, James Webb also looked at an exoplanet called WASP-96b. And this WASP-96b, it's a hot exoplanet, which is at this distance in a certain constellation. And what it basically did is it observed its light curve, exactly what we were doing in Kepler data. It observes its light curve, got its fall, right? And got its values. And then it also did another job, which is of taking the spectrum of this thing. So actually the light curve it didn't do. Light curve was already there from Kepler data. What James Webb did is it took the spectrum of this thing. And with this spectrum, it actually detected water, right? So James Webb telescope actually detected water on this source, right? And therefore, this source is going around a sun-like star, and therefore it's a gas giant, but it seems to have water on it. Now, James Webb, therefore, now we see is a very ideal telescope to study exoplanets. And therefore, there's a set of 20 exoplanets which James Webb is supposed to study. In the sense, take the spectrum of those exoplanets and study it. Okay. And therefore, there is a contest which has been fixed up, which is called the NameExoPlanet contest. Okay. And I'm going to show that to you. I've shared this website also. So it calls, this is earlier also the International Astronomical Union, the IAU. They had organized NameExoWorld contests where people could actually offer names for planets. So it was earlier done in 2019. It was also done in 2015. So thus now we are seeing the 2022 edition of NameExoPlanets. If you see in this, they have given us a list of 20 exoplanets. Okay, I'm going to share that with you. And what you all have to do is we will make a team called Gargi College team. Okay, now Gargi College team, I will give you all the, you have to basically, there are 20 star planet systems for which you have to suggest names. Okay, now how do the names, all countries of the world will suggest these names, right? And they could be names from mythology, from some stories, from some cultural context, right? They could be different kinds of things which are typical of that, of the place. So for example, I had an example over here. This is one of the earlier ones. I hope you can see the video. This is the video of, this is the ExoWorlds which were offered, I think, by Italy. It's not playing. Okay, it's not playing. But in short, you can offer. It's not playing. Okay, no problem. So you can offer some names depending on this thing. So I have some examples over here where I have actually shown some of the names that people have given. There are certain rules. So how do we participate? Create an outreach event. That is the event we had today. And this is the one that you'll have. Now what we do is we have a team. We'll make a team of 10 people whom Vandana ma'am will make up. And along with that, the team will actually ask people to propose names. And finally, of the names which are suggested by people, the team will select names. Okay. And once they select the names, then you will have to submit the names via a form, which is given over here. So what you'll actually have to do, you've got to see the naming rules. How are the names to be done? They should be things or places of long-standing cultural, for example, I don't know, you can call it Delhi, Agra, for example. If you have a star and an exoplanet, say you call the star Delhi and you call that place Agra, for example, because you're in Delhi. Or it is from some themes related to sky and astronomy. You can see which constellation this star is, etc. According to that, you may do. You have to basically propose two names, one for the star and one for the exoplanet. And there are certain lists over here, what is excluded. You cannot take the names of real people, right, living or dead. You cannot take the names, you can't have any acronym. You cannot have names of pets animals. You can't have names of organizations. You can't have names of which have numbers, punctuation marks, or political, military things you can't have. They should be that it should not be a trademark. You can't call it like Godrej or something like that, which is a trademark. You can't take the mix of two words. For example, you can't say lion rock, right? So you have to you cannot take names which are already accepted names of the IAU. So for example, there's a list of IAU accepted names which is given in this link. I'm going to share with Vandana ma'am. I've already given her this list. So you can't give names like these because these are already names which have already been made by IAU for other things. So you can't choose those names, right? So you are going to choose your names and we are going to, this is the committee. Once you send your names, these are, you go into 2022 ExoWorlds. These are the ExoWorlds, right? And if you click on this, you'll see the names of each of them. So for example, let's go in this one, WASP. Okay, let's take WASP, say let's WASP 69. This is in constellation Aquarius. So you may go inside this. Here it's telling you properties of the star. The star is like this. It is a star of temperature 4,700, distance of this, mass is this. The planet is a planet which is at a temperature of 960 degrees Kelvin, right? It has these things. You can further click on this and it's going to give you even more details about the planet. So for example, it's giving you an artist impression, what they think the planet, it's a hypothetical visualization of what it looks like, a giant planet composed mainly of gas. It's this, it is like this. And you can put a name for it. Similarly, you can go and check out any other of the exoplanets which are mentioned over here, right? For example, you take this one. You can see all of them are single star with single planet, 1:1. So you have to use this. See the properties. See, this is 1000 degrees, 7,900. You either use, for example, you can use the temperatures, if it's hot or it's cold. You can use the name of the constellation, Karina. See what is Karina called in Hindu mythology, in Indian, in Hindi, in Sanskrit. Can you find some objects which are related to Karina? For example, Karina in Hindi or in Sanskrit. I don't know. I don't know. So you'll have to check what is Karina constellation in Hindi. Achha, it's still saying Karina only. So you'll have to check up what is it called in Hindi, right? And maybe based on that, you can choose the name or you can choose it as you wish, right? So we are participating, Gargi College hopefully is participating in the competition. Vandana ma'am will share the this thing. If you forget this thing, you just have to Google, just say NameExoWorlds, okay? If you say NameExoWorlds, you'll immediately get it. IAU NameExoWorlds. And once you click on this, go into the 2022 edition. And here all the rules are there. What is the method or what are the naming rules? Please be careful about the naming rules so that you don't give a name which is not allowed, right? Be very careful about noting which are the ones which are excluded, right? You should not have any of these excluded names, right? please be careful in choosing names which are nice, right? Vandana ma'am will share with you a Google form in which you can enter your names, you can give your names, and then the Gargi team made up of 10 people will actually, what do you say? They will actually choose the ones they want, and you all can actually submit your thing. So that would be a good conclusion to this event which we've had, where you all can actually do your naming of ExoWorlds, right? So I'll stop over here and I'll again take another set of questions if you all have any. Sharing the screen, I'll stop sharing. And yeah, Vandana ma'am, we can take any questions. There's a feedback form. I'm sorry I ran through things, but I didn't have a choice. I will
But
share with you.
But I think students will be able to pick it up from whatsoever information you have shared with us, and they will be keen to work further on that.
Yeah, I will share, like I told you, I will share you a very detailed, I'm just now going to share that to you, a very detailed video which has, which has this in a lot more detail. The whole thing is done in 2 hours. So that will be easy for people to follow, right?
Actually, it will be also provide a connect between the physics laws, concepts, and to this exciting world. So I
Yeah.
think students will be surely interested in that. And thank you so much for that. I think there are no more questions at the moment.
Yeah.
So we can conclude this session, Dr. Priya.
Yeah, sure.
Yeah, so thank you so much for this exciting talk detailing about exoplanets ranging from rocky planets to hot Jupiters. And you also included in your talk the methods of detection employing the laws of physics like Doppler effect, beautiful depiction of red and blue shift, and the changes in the spectra. Methods you discussed were radial velocity, microlensing, direct method, and the transit method. And also you discussed about the difficulty in measurement at different levels. It was just walking through a journey from their discovery of the first planet to more than 5,000 till today. And the mysterious theories of, say, planetary migration, which I think students will be interested to explore even more. The information from the light curve about the system can be used for understanding the properties of the star planetary system, and planets with bigger wobble can be identified as compared to less wobble, and a contrast between ours and exoplanets were also discussed in this talk, and also about formation of planet and star and the planet formation. Such an engaging session on analysis with the Kepler's data. We had all the guidelines in which students can take it up further, and the participation in NameExoWorlds will surely provide a unique opportunity for the students to get more engaged with the topic. So indeed a wonderful session, and now I invite Professor Chawla for proposing the vote of thanks. Thank you so much.
Thank you, Professor Vandana. And thank you, Dr. Priya, for enlightening me at least about the exoplanets. So thank you very much. Now, and it is my pleasure and privilege to propose vote of thanks for today's talk. I would like to thank our principal, Professor Sangeeta Bhatia, for her immense support and inspiration for organizing this webinar. My heartfelt gratitude to our esteemed speaker of the day, Dr. Priya Hasan, for accepting our invitation and giving such an insightful talk. We are sure that this session has enlightened our students, faculty members, and other participants about the exoplanets and like how to name them. I would be really very happy to name at least one of the exoplanets. Then this opportunity was provided to us by National Academy of Sciences, India. I and Professor Vandana are thankful to the Academy for giving us an opportunity to conduct diverse activities under NASI Science Society program. And this is for the benefit of society under this unique Science Society program. So I'm grateful to our mentors also, who are Professor Ajoy Ghatak, who is President NASI, and Professor Anurag Sharma, Vice President NASI and Chairperson NASI Delhi Chapter. A special mention is also about the officials of NASI, Prayagraj, for all the support they provide to us. Then thank you to Mr. Anuj, who is here in Gargi College for the technical support he's provided, and lab staff for administrative help. Also to all the participants for sparing their time for attending this talk. At the end, thank you everyone for participating in this webinar. And thank you, Dr. Priya. Thank you so much for coming here and helping us.
Thanks a lot. Thank you so much. And thank you, everyone.
Yeah,
I think
thank you
this
so
is
much.
just a beginning, and you will find more people interested in it, and they will be interacting with you in forthcoming sessions also. Thank you so much. Thank you, everyone.
Thank you.
Thank you.
for the
Thank you so
session.
much. Everybody,
Thank you.
thank you.
Thank you.
So I think we can wind up now.
Yeah.
Yeah. Bye, everybody.
Bye.
Bye, everybody.